All right, so today we're going to mostly be working on function notation lessons 3 and 2, okay? Our learning goals for the first lesson are learning what a function is in mathematics and learning how to use function notation. So we have looked at many different ways to define a relationship in math, even like in elementary school, but basically in grade 9 and 10 we looked at a table of values, a graph, and an equation, okay, as ways to define a relationship. A function is another way to define a relationship. Its definition says that it's a mathematical relationship that assigns a single output value or a y value. So single output value meaning y value for each x value. So for each x value, there's just one y value. Okay? Many relationships we've learned about in grade 9 and 10 are functions, and another one we learned about in grade 10 is not a function. Okay? And we're going to look at the graph right now to help us out. Examine each relationship and decide whether or not it is a function based on this definition up here. Okay, so x-axis are our input values. So here's our input values, kind of thick, but they're always on the x-axis. So these are our valid inputs. I'm just going to write x beside that. So these are all our x's. For each one of these x's, do you see that there's only one corresponding y value? Any x I pick, there's only one corresponding y value. Did you see that? So this would represent a function then, okay? Here's a circle. I'll use a thinner highlighter here. So for my circle, these are the only valid inputs. Do you agree that this wouldn't be a valid input over here? Because there's no output? Okay, so these are my valid inputs. And for each one of these inputs, well, for this one, there's only one. But say I'm looking here, there's two outputs. Does everyone see that? There's two y values for one x. So this, by definition, is not a function. So circles are not functions. So as soon as you break that rule one time, you don't have a function. If you can find one x value that has two y values, it's not a function. Okay? And here is a parabola. So here's my valid x values, those are all my valid inputs along the x-axis. Okay, pick any one at random. So if I pick this x value, its corresponding y value is going to be down there somewhere. Okay, but do you agree there's only going to be one? All right, and here, there's only going to be one corresponding y value. Way over here, there's going to be one, but it's going to be way down there somewhere. Okay, so for every x value, there's only one y value. So this is a function. Now, instead of giving us a graph, they give us an equation. So if they give you an equation, it must be one you know. So it must either be a line, a parabola, or a circle. Those are the only three you know from grade 9 and 10. Okay, so how do you tell whether this is a line, a parabola, or a circle?
The exponent on the x.
The exponents on the x and y. Awesome. Let's do black here. So there's an exponent of 1 there, and an exponent of 1 there. So if x and y both have an exponent of 1, it's a line. Okay? And think about lines in your head. Let's do a not draw this one specifically, but let's draw some lines. There's a positive sloping line. There's a negative sloping line that's less steep. What else? What other lines are there? There's a horizontal line. And there's a vertical line. Positive sloping lines, are they all functions? So for every x value, there's only one y value. Everyone agree there? My x values are all along the x-axis. Okay. How about negative sloping lines? Are they all functions? Yep. How about horizontal lines? Are they all functions? So every x value has just one y value. It's always the same y value, but this every x value just has one y value. So they're all functions. How about this one? There's only one valid input for first of all, right? This is the only valid input right there. The only input that gives you an output. And how many outputs does this one give you? An infinite number, right? So is a vertical line a function? No. So only one type of line that's not a function. And vertical lines have special equations. Think back to axes of symmetry. Their equations always look like this. X equals a number. So this one could be like x equals 5, for instance. Okay? And that's not what this one looks like. So it's either got a positive slope or a negative slope, so it's a function. Okay? All right, so another equation, so it must either be a line, a parabola, or a circle. Anyone? Yep. Parabola. And because the exponent on where the x is a 2, okay? And the exponent on y is a 1. Okay, so this is a parabola. Oops. Parabola. What do we know about parabolas in general? They open upward. Are they functions? Yes. Every x value, which are here, has only one corresponding y value. Everybody good? Okay. And if they open downward, there's only x values, and I'm only ever going to have one corresponding y value again. So if they open up, if they open down, they're functions. So this one, if it opens up, it's a function. Okay. F, another equation, so it must be a line, parabola, or circle, because those are the only ones you know from grade 9 and 10. This one is a? Nope. This is a circle, good. Yeah. So this one's a circle because both x and y are squared. Okay. If you forget about circles, the general equation is x squared plus y squared equals radius squared. So this specific circle has a center of 0, 0. And since radius squared is equal to 25, the radius would be 5. You square root both sides. So this would be like 5, negative 5, 5, negative 5, looked at a circle, we know that the valid inputs are along the x-axis here. And the majority of them have 2 outputs, so it's not a function. Okay? Okay? So either be given a graph, and then you can use the definition to figure that out, or you'll be given a equation, and it has to either then be a line, a parabola, or a circle. Something you know. Okay? Can you make some generalizations about lines, parabolas, and circles and whether or not they're functions? So we know all lines except vertical lines are functions. All parabolas that open up or down are functions. And all circles are not functions. So on our 3 things we know from grade 9 and 10, we can make some important generalizations there. Every single line, unless it's a vertical line, is a function. All parabolas that open up or down are functions. All circles are not functions. Okay. How can you tell from a graph whether a relationship is a function? It's called the vertical line test. So you can see I'm showing a vertical line that goes through more than one place on the graph. So we know that circles are not functions. And then they're showing a vertical line, no matter where you put it, it's only going to touch in one spot. Okay, so there's a visual of what the vertical line test is. If you want to write it out in words, the vertical line test states that if any, hi, no. Okay, thanks. Yeah, you too. The vertical line test states that if any vertical line touches the graph in more than one spot, the graph is not a function. So the vertical line test states that if any vertical line touches the graph in more than one spot, the graph is not a function. Okay, so it's kind of a quick test that you can do with either your pencil, ruler, pen, okay, finger. So if we go back to the ones that we did originally, here, so I could take this ruler, I guess, that's my vertical line, and then pass it along, not as small as possible. And no matter where I put it, it's only going to touch the graph in one spot. Okay? Here, I can see right away. Oops. Not good with spatial perception. There we go. Touching in 2 spots. It's a good angle. As we move it along here, well, I guess it depends on where the light is. 1 spot, 1 spot, 1 spot, 1 spot. And then this one was our one that didn't work. touches all the way along. I have all the other ones. Only touching one spot. There we go. Okay. Great. So that's kind of from a graphical perspective, and then equations that we can picture as graphs of how to tell whether something's a function or not. What makes a function special, a special relationship, is that each input x results in only one output y. Functions are special relationships, and mathematics came up with special notation to work with them. Okay, so consider the linear function y equals 2x plus 3. So most of us hopefully remember from grade 9 that this would be a line. Okay, it has that mx plus b look to it. Y and x both have an exponent of 1. So rewriting this line using function notation, we replace y with f at x. Okay, so that's function notation there. And what does it stand for? F is a function of x. It doesn't mean f times x. Those graphics do not mean multiply. It's just notation. Okay. And it means f is a function of x. Just like here, if I wanted to, I could say y is a function of x. Okay. So f at x and y mean the same thing. They're just written differently. Okay. So when you see f at x equals 2x plus 3, it's read f of x is equal to 2x plus 3, or f at x is equal to 2x plus 3. It kind of depends on the textbook and your math teacher whether you say f of or f at. I was taught f at, so I'm going to say f at. Okay. Mr. Salawiga, I believe, says of. Okay. So that won't really bother you in grade 12. At or of doesn't make a difference. If function notation is used correctly, it should only be used for functions. So that's another good thing about it. That's why it's important for calculus, because it says what comes next is a function. So I wouldn't use function notation for a circle. I would use it for something that is a function called. Okay. So function notation is similar to an equation. So we're going to practice using it. It's pretty easy to use once you get the hang of it. Okay. So f at x equals negative 3x plus 7. So again, f at x takes the place of y, so really this is just a line again. Then find each of the following. So f at 2 means you're going to replace each x with 2. Okay, so here's my definition. F at x equals negative 3x plus 7. So f at 2 is going to be negative 3. Now when I replace x with 2, I'm going to use brackets, plus 7. So f at 2 is going to equal negative 6 plus 7. So f at 2 equals 1. Okay. And remember that this means when x is 2, y is 1. So this really means that the point 2, 1 would be on the graph of that. Okay? So my input is 2. And then I do the work and get my output, which is 1. Okay, so x represents input, y represents output. So if I were to graph this line, the point 2, 1 would be on the line. Okay, so similarly here, f at 3 is going to be negative 3 times 3 plus 7. So f at 3 is going to be -9 plus 7. So f at 3 is going to be -2. And again, that means, you don't have to write this down, but it means that when x is 3, y is -2. When the input is 3, the output is -2. So if I were drawing that line again, I would expect the point 3, -2 is going to be on that line. Okay? F at 1. So I'm going to replace x with 1. That's going to mean the point 1,4 would be on the line. We'll test this out because you've got a graph below here. F at 0. -3 times 0 plus 7. And that's just going to give you 7. And then try E. Try to find f at -2. Watch the two negative signs. Okay. All right, so now let's put this information onto a graph. So if we were to plot f at x equals -3x plus 7. It's the same as drawing the graph of y equals -3x plus 7. And we would recognize it was a line that had a y-intercept of 7. And then a slope of -3, which is the rise over the run. So from that y-intercept, we would go down 3 and right 1 to get more points on the line. And reverse it, going the other way. And then draw our line in. Zeros on the end. And then if you look back at the function notation we did, we should see these points on our line. 2, 1. 2, 1 is right there. Okay. And then 3, -2. It's right there. And this one would be 1, 4. 1, 4 is right there. 0, 7 is right here. -2 and 13 right there. So It is just another way of writing the equation of a line. That's all it is. Another way of writing it. Okay. Says what about f at negative 2/3? We're still going to do the exact same thing we did up at the top. So we're still using this function notation. So we replace x with negative 2/3. And then we have to remember how to multiply a whole number by a fraction. If you forget, you change the whole number to out of 1, and you multiply the tops together and the bottoms together and reduce. So that's going to be positive 6 over 3. Six over 3 is actually 2. So f at negative 2/3 is actually 9. See if that makes sense with your graph. So our x is negative 2/3. So our x is negative 2/3, which is about here, and our y is 9. So that would be that point right there. Negative 2/3 and 9. Make sense? Okay. Great. All right, so now if f at x is 2x squared minus 5, find each of the following. So instead of just a linear equation, we now have got an x squared or a quadratic parabola. Okay. So when we substitute that x in, it's going to have a square. So we're going to do the exact same thing. So f at negative 2 is 2 times negative 2 brackets squared minus 5. Make sure you use BEDMAS. So before you multiply by 2, you have to do the square first. In fact, some people are rusty on that and forget that early on. So you'd have 2 times 4 minus 5. Because negative 2 times negative 2 is positive 4. Okay, remember, whenever you square a negative, you get a positive. If you're using a calculator, make sure you can enter it into your calculator correctly. And some of you might just enter this into your calculator, like write it down and then go straight to the answer. That's fine. So if you can enter that into your calculator and go straight here, that's fine. Okay? So f at negative 7, so we're replacing x with negative 7. So it's going to be 2 times 49 minus 5. Which is going to be 98 minus 5. Which is going to be 93. Try with a 0. Two times 0 squared minus 5. multiplying by 0 gives you 0, so it would just be -5. You get there? Okay, and then our trickiest one is a fraction. So one thing I would do is I get to choose whether I put that negative out front like that with the top number or with the bottom number. Whenever you're working with a fraction, I always put the negative with the top number. So then we're going to follow BEDMAS, which means we're going to square this fraction first. So you have to remember, when you square a fraction, you square the top and you square the bottom. So -9 squared is +81, and 2 squared is +4. Okay, so don't forget to square the bottom, that's a common error. Square the top, square the bottom, and remember when you square a negative number, you get a positive. So following BEDMAS, I would do the exponent first. Okay? Then I would do this multiply here, but I would make 2 out of 1, and then multiply the tops together and the bottoms together. So that's going to give me 162 over 4 minus 5. And then I see what 162 divided by 4 is. What is it?
40.5.
Thank you. Which is 35.5. If it didn't turn out to be a 0.5, like if it was a 0.3 repeat, you'd have to leave it as a fraction. Okay? And then subtract the fraction. I'm sure we'll get to examples like that in this. All right, E, solve for x if f at x is 13. So a little star beside this one. A little bit of a thinker here. So we know from our definition that f at x is 2x squared minus 5. So this question's set up differently. It doesn't say find like f at 5, for instance. It doesn't say that, where we know we sub 5 in here to get the answer, here and here. Instead, it gives me f at x. It gives me a number to put in over on this side, and it says, what's x if f at x turns out to be 13? Okay, so it's like a backwards question. So you're going to replace f at x with 13, and then solve for x. Okay? I'm saying what value or values of x would give you an output of 13. Okay? What value or values of x would give you an output of 13. So we can see the x is only in one spot, so I can use reverse BEDMAS in order to get x by itself. So I'm slowly trying to get that x there by itself. What would be the first thing I would do to both sides? Yep.
Add 5.
Yes. So I undo any adding or subtracting first. Okay, so I created a 0 pair there. And then I have 18 on this side. What would I do next? Divide both sides by 2, so I undo the multiplying, dividing. So that's going to give me 9 equals x squared. Next up. Yep.
Square root both sides.
Square root both sides. That undoes the exponent. And remember, you have to put a plus or minus. It's a quadratic because x is squared, so you need the plus or minus in front of the square root. Think about the quadratic formula when you're solving a quadratic equation. There's a plus or minus right in the formula. Okay? So then that's going to tell me that x, so here's my x, is either positive or negative 3, because the square root of minus 3. Okay? So your solutions are either x equals 3 or x equals negative 3. Which means if I put 3 in here, I would get 13 out. And if I put negative 3 in there, I would get 13 out. Okay? And you can think it through. If I put 3 in, 3 squared is 9, times 2 is 18, minus 5 is 13. So you can check your answer when you're done. Make sure it makes sense. Okay? All right. Given the function, it's quadratic again, f of x equals negative 2x squared plus 4x minus 5. Find each of the following. Okay, so try f at negative 3 on your own. You should like to try that. Okay, so I see tons of people wrote the notation down. They've got f at negative 3 equals negative 2 using brackets. Okay, some people will be able to go to their calculator and get the answer now. Other people will do it a step at a time. That's fine. As long as we all arrive at the same destination. Negative 35. Yep. Any questions? Anyone get something different? They're not sure what went wrong? Remember, when you square a negative, you get a positive. That's usually the most common mistake. Okay. All right, now this one's got a little twist because it's not just f at 2, it's f at 2m. So let's see what's different about this one. Okay, so f at 2m is going to be negative 2, replace x with 2m squared plus 4 times 2m minus 5. So that's your first stage. That's just showing you know what function notation means and how we choose it, what it looks like. Okay. Now we'll simplify this as much as we can, but it'll turn out we can't simplify it nearly as far as we can simplify that one, because we're going to end up with terms that aren't alike. Okay. But we're still going to do what we can. So we can square 2m, but be careful. When you square 2m, it's 2m times 2m, which is 4m squared, not 2m squared, which is a common mistake. Okay? Make sure you think that through. 2m times 2m, 4m squared. Here I get plus 8m minus 5. But I'm not done because I still have to do this multiplication here. Remember to use BEDMAS so that you square before you multiply. That's another error. Oops. And then you have to realize that you can't go any further than this. I know it's tempting because all the other ones we've been just a number answer. But we've got a term that has an m squared ending, an m ending, and a plain number. So they're not, none of them are like terms, so you can't go any further than that. So that's f at 2m. Okay? F at 5k. Well, let me write the rule up. You don't have to look backwards. So there's our rule, our f at x. So try f at 5k because it's a lot like the one we just did with the 2m. Remember that 5k times 5k is 25k squared, not 10k squared. So that's going to end up giving us negative 50k squared plus 20k minus 5. Yeah? Make sense? Okay, awesome. All right, f at 2/3. Try that one. Get some practice with fractions. Leave them as fractions because we're in thirds now. And then where you get stuck, we'll pick up and you can see what you weren't remembering. Square the top, square the bottom. So when you square a fraction, you square the top and the bottom, so you get 4/9 there. If you're going to do this multiplication now, remember that it's top by top, bottom by bottom. So it'd be 8/3 minus 5. Now we're going to do this multiplication. It's top by top, bottom by bottom again. So now you've got fractions and a whole number to add together. Who remembers how you do that? Like to get a common denominator. So your denominators are 9, 3, and 1. So the common denominator is 9. Okay? So you're going to make each of these fractions out of 9 or into ninths. And then if the denominator wasn't 9 originally, you have to adjust the numerator. Okay? So this one already had 9 for the denominator, so negative 8 is going to stay. But for 3 to get to 9, I had to multiply by 3 here. So I have to multiply by 3 there too. So that's going to give me 24 ninths. And to get from 1 to 9, I had to times by 9. So same thing. 5 times 9 is, sorry, that should be a negative in the middle there. 45. We'll correct that. This is a minus here. Okay, so now I would do, now I'm all in terms of ninths. So negative 8 ninths plus 24 ninths is 16 ninths, and then minus 45 ninths. So basically you could do negative 8 plus 24 minus 45 on your calculator, and then you know you're in terms of ninths. Okay. So you end up with negative 29 ninths. And then you could check and see if it reduces, but this one doesn't. Okay. And then E, I put a star beside this one because there's a really common error, misunderstanding that people have about this one. So f at x plus 2 is going to be negative 2 times x plus 2 squared plus 4 times x plus 2 minus 5. And the big misunderstanding that people have is they think that x plus 2 squared is equal to x squared plus 4, but that is not true. They're not equal. When you square x plus 2, you have to times it by itself using FOIL, you may have called it, or multiply each term in the first bracket by each term in the second bracket. Okay? So then you'll actually end up with 3 terms. Let me simplify it there, not just 2. Okay, so when you're doing this one, on my first time through, I would just expand, so I'd write that as x plus 2 times x plus 2. Here, you can do the distributive property there and get plus 4x plus 8 minus 5. But in this term, the next thing you're going to do is multiply those two binomials together. So I'm going to keep the negative 2 out front, and I'm going to do x times x. And that gives me x squared. And then I'm going to do x times positive 2. And that gives me positive 2x. And then I'm going to do positive 2 times x. And that gives me positive 2x again. And then I'm going to do positive 2 times positive 2. Positive 4. Close my bracket. So all I did there was the exponent, but I had to multiply x plus 2 by itself. And then I've still got the plus 4x plus 8 minus 5. Okay? Then a lot of people, next, they like to simplify inside the bracket by collecting those like terms there. So 2x plus 2x is 4x. And now finally you can do the distributive property here. And multiply that -2 by each term inside the bracket. And once you've done that, then you want to look and see if you've got like terms, which you should. So it's going to be -2x squared minus 8x minus 8 plus 4x plus 8 minus 5. So there's no other x squared term. And then -8x plus 4x is -4x. And then -8 plus 8 minus 5 is -5. So that would be your final answer. That took a lot of steps to get through. Stuff that we kind of already know from grade 10, but we may be a bit rusty on. Okay. All right. So take a deep breath. Now we're going to do the fraction ones. And we're going to continue the fraction ones in our lesson 2. Okay, so if you're feeling anxious after this, don't. We've got the whole day to get comfortable with the fraction ones. Okay. All right. So given the function g at x, so instead of f at x, you could use the letter g. Often they'll use g if you're talking about two functions in the same question, but it doesn't mean anything different. Okay. So it still means we're a function. Okay. So g at -1, if this is g at x, start off pretty easy. We're going to replace x with -1. The only reason I didn't put it in brackets was because there was nothing out in front of the x. The x didn't have a number out front. You can still put brackets if it makes you feel safer. So g at -1. So when you have a fraction, you want to before you divide, you want to simplify the denominator. So -1 minus 3 is -4. And then that's a fraction. I just see if I can reduce it to lowest terms. Okay. So in this case, lowest terms, if I divide top and bottom by 2, I get -1/2. And the negative can go with the bottom, out front, or with the top. I always put it with the top. Okay, so that one is fairly straightforward. Now we're going to ramp it up a bit. So it's still going to start off the same, where we replace x with 1/4. So now I've got what I call a 3-layer fraction, okay? And a 3-layer fraction is never considered to be simplified, okay? So I'm going to look at the denominator, and I'm going to do that subtraction, okay? So I'm subtracting a fraction and a whole number in the denominator. So I still have 2 way up in the numerator here. But in order to subtract here, I need a common denominator in the denominator. Okay? So what's my common denominator going to be? Between 4 and 1. 4? Good. So I'm going to make each of these out of 4. the subtract in the middle. 1/4 already had 4 as its denominator. The 3 had a 1. So to get from 1 to 4, I had to multiply by 4. So I have to do the same thing with the 3. Okay, whatever I did to the bottom, I had to do to the top of the fraction to make it equivalent. Okay, so now that we have, we're in fourths in our denominator, we can actually do the subtraction now. 1/4 minus 12/4 is negative 11/4. Okay, still got a 3-layer fraction, so that can't be my answer. But there's a rule for dividing by a fraction. So this is a divide symbol, and in the bottom we have a fraction. Who remembers the rule for dividing by a fraction? Yep. Multiply by the reciprocal. Good. Flip and multiply, or multiply by the reciprocal. So you keep the first or the top the same, whether it's a fraction or not, and multiply by the reciprocal. I always just leave the negative with the top. Reciprocal means flip, okay? Multiply by the reciprocal. So you've changed the dividing question into a multiplying question. And multiplying is multiply the tops, multiply the bottoms, reduce. So that's going to give me negative 8 over 11. Which doesn't reduce, but now it's just a 2-layer fraction, and so that's my answer. Okay, we've got 2 more, getting a little bit more complicated each time to go, and then we're done. Lesson 1. Oops. As I go, they're not there. Maybe they're 2 away? Yeah, there they are. Okay, so our rule is g at x equals 2 over x minus 3. So you don't have to flip back. All right, so g at 1 over 5x. Got a lot of room, so I'm just going to rewrite this here. The 2 stays on top. I'm going to replace x with 1 over 5x. And then the minus 3 is going to stay the same. So that's my step where I just show that I understand what using function notation means. The rest of it is going to be trying to simplify this so I don't end up with a 3-layer fraction. Okay? Okay, so if I look at the fractions in the denominator, one's got a denominator of 5x and one's got a denominator of 1. So what's the common denominator? 5x. Good. They're both going to be out of 5x all of a sudden. Okay. So this first fraction already had 5x as its denominator, so its numerator is going to stay the same. But the second one, it had 1 for the denominator, so I had to multiply it by 5x, which is exactly what I'm going to need to do to the top. So I'm thinking, what's 3 multiplied by 5x? It's 15x. Okay, 3 multiplied by 5x is 15x. Okay. So I've still got 2 in my numerator. Now, 1 minus 15x, one's got 1 and one's got an x. They're not like terms. Does everyone agree? So the only thing I can do, since they're both out of 5x, is I can subtract them, but that's the best I can do at subtracting them, is write it as 1 minus 15x. Okay. Still got a 3-layer fraction, so the same rule is going to apply. I I'm going to keep the first fraction the same, and it's just a 2, and then multiply by the reciprocal of the one in the bottom. So 2 divided by this is the same as 2 times it flipped upside down. And the 2 really has a denominator of 1 there. So if I multiply the numerators together here, I get 10x. And if I multiply the bottoms together, I get 1 minus 15x. And now I've got a 2-layer fraction. So now it's considered simplified. Okay? And our last one for this morning. So again, the first step is just to replace x with whatever g is at. So it's going to be 2 over, replace x with 1 over x plus 5 minus 3. Okay, so this, and this should all be the same. So replace x with 1 over x plus 5. That's just using the function notation. Okay? So now I have a 3-layer fraction, and that can't be my answer. So I look at my 2 denominators and decide on a common denominator. So one of my denominators is x plus 5 and the other one is 1. If you're never sure of a common denominator, you can multiply them together. Okay? So 1 times x plus 5 is just x plus 5. Oops. I'm going to make each of these out of x plus 5. The first fraction already had x plus 5 as the denominator, so the numerator is going to stay the same. The second one had a 1, so I had to multiply it by x plus 5, which means I have to multiply this by x plus 5. And I want you to show it like that using a bracket for now, okay? I'm going to kind of try to insist you do it my way because it's the least, or it has the best outcomes for getting the right signs everywhere. So that would be the first thing you would do. Still got the 2 at the top. Now I want you to write this stuff in rather than doing it in your head. So subtracting over the common denominator. Okay, subtracting over the common denominator. I call this my start step. This is a really important step into getting the correct signs everywhere. Okay? So now, if you follow BEDMAS, you're going to multiply next. So you're going to keep the 1, and you're going to multiply negative 3 by x, you get negative 3x, and you're going to multiply negative 3 by positive 5, you get negative 15. Okay? So you're going to keep the 1, multiply the negative 3 by x, and get negative 3x, and multiply the negative 3 by 5, and get negative 15. And that's still out of x plus 5. And then after you've done that step, you'll find like terms on the second level that you can combine. Okay? So that's going to give me 2 over negative 14 minus 3x, or you can have negative 3x minus 14, doesn't matter. okay? Over x plus 5. And now we're just on our last step where we flip and multiply. So we keep the first fraction the same, which is a 2, and multiply by the reciprocal of the second. And then, rather than multiplying the 2 through using the distributive property, you can just leave it like 2 brackets x plus 5 over negative 14 minus 3x. Okay? It's not wrong to do 2x plus 10. It's just, especially in calculus, you'll be going towards simplified factored form, so you don't have to do that multiplication. Okay, so hopefully given an input or an x value, you can correctly substitute into function notation to find the output, identify a function from its graph, understand the relationship between the graph and function. All right, so I got practice 1 for you. Proposed solutions in a minute.
I remember the word. Thank you, Ben. I remember the word. So good.
Oh, I got to stop. Okay, so stop recording.